Swayam Prabha. Digital India. Educated India.
The next question we ask ourselves is that what is the shortest lattice translation vector for this centered rectangular lattice. So, we have the centered unit cell of the centered rectangular lattice, and clearly neither A nor B is the shortest lattice translation vector, but it is actually half the diagonal of the unit cell, which is A plus B by 2, which is the shortest lattice translation vector. The shortest lattice translation vector is an important quantity, and we will deal with it later, when especially in the context of dislocations, wherein this shall play the role of the Burgers vector. The fourth lattice we consider is the 120-degree rhombus lattice. As you can see, it is not just any rhombus, but a rhombus with an included angle of 120 degrees. In this picture, we can see the 120-degree rhombus lattice. Also overlaid on the lattice is the lattice translation vectors A and B with an included angle which is 120 degrees, and also the unit cell of the lattice. The lattice parameters for this lattice are A equal to B, which is why it is called a rhombus, and the included angle alpha is equal to 120 degrees. On the right hand side of this lattice is the same unit cell with some symmetry elements overlaid on it. As before, we have not overlaid all the symmetry elements, and that is for the sake of clarity for you to understand the essentials of this lattice. Clearly, there is a six-fold axis. There is also a three-fold axis which is at the centroid of the triangle, which is half the rhombus unit cell. There is also a two-fold which is at the half the distance of the diagonal. Let us look at this lattice unit cell a little more carefully, looking at the figure on the right hand side. Herein we have overlaid all the rotational symmetry operators onto the unit cell. So, there are six folds at each vertex of the unit cell, and inside the unit cell at the centroid of the triangles are two three-fold axes, and at every edge center there is a two-fold axis, and additionally along the diagonal center there is a two-fold axis. One question which sometimes people who have read some textbooks might ask is that sometimes there is a representation of the same lattice without the six folds. How is this possible? Clearly we can see from the lattice and from the symmetry of the lattice that the lattice has a six-fold symmetry. Yes, there are additionally three-fold axes, but this three-fold axis is in addition to the six-fold and not at the expense of the six-fold. We will try to answer this question very soon. Now, on the same unit cell, suppose I overlay the mirror symmetry operators, that is, in addition to the rotational symmetry operators, I am overlaying the mirror symmetry operators, and that is what has been shown on the figure on the left hand side. So, you have the original six-fold axis, the three-fold axis, the two-fold axis, and additionally there are these red lines which are mirrors in this lattice. So, you can see the cell edges are mirrors. There are these vertical mirrors, and also which are equivalent to these inclined mirrors also. The long diagonal and the short diagonal are also mirror planes. To write a shorthand notation for the symmetry of this kind of a lattice, we write it as 6 mm, wherein the first mirror can be considered as this mirror, and the other mirror is the diagonal mirror, which is inclined at an angle of 30 degrees to the original mirror. The other mirror, which is at 60 degrees to the original mirror, need not be considered or written separately, because that will automatically be generated by the rotation of this original mirror, say for instance this horizontal mirror, by the six-fold axis. In other words, the six-fold axis will take the horizontal mirror to the mirror which is inclined at the angle of 60 degrees, but this mirror is not related to that mirror and has to be listed separately. So in other words, this would constitute a mirror 1, and this mirror at 30 degrees to the original mirror would constitute the mirror 2, and the shorthand notation for that would be a 6M1M2, or even more concisely a 6mm symmetry. And just to re-emphasize the fact, we have redrawn the lattice here with the shortest lattice translation vector. As you can see, also in this case, the shortest lattice translation vector is neither the A vector nor the B vector. As we already know, the modulus of the A vector is same as the modulus of the B vector, but they are inclined at the angle of 120 degree to each other, and the shortest lattice translation vector is the vectorial sum of A and B and is along the diagonal of this rhombus, which is shown here in this figure. So we have identified the shortest lattice translation vector, we have looked at the mirror symmetries and the rotational symmetries of the 120 degree rhombus lattice. An important question which comes to mind when we are dealing with such lattices is the fact that when we consider a 120 degree rhombus unit cell, the rhombus unit cell itself does not have any six-fold symmetry, and often when you are reading textbooks you might have come across a unit cell which looks like this yellow unit cell which has got a six-fold symmetry. So the question which comes to mind is that why are we using this as the cell for this lattice, and more importantly, what is the role of this yellow shaped cell for this hexagon shaped lattice. So let us consider this hexagon shaped lattice. This hexagon shaped lattice is in fact a composite of 3 unit cells or 3 cells of the original type, but they are all not along the same orientation. They are in fact rotated with respect to each other. For instance, this yellow unit cell is rotated with respect to this yellow unit cell, which is further rotated with respect to this yellow unit cell. But the whole composite six-fold unit cell is a combination of these 3 unit cells. Now, if we try to calculate the number of lattice points per cell for this larger cell, we see that the lattice points at the vertices of this unit of this cell actually make a contribution of 1/3 to this larger cell, and therefore the net contribution from 6 of these is 2. The lattice point at the center of the cell makes a complete contribution, which is a full contribution to the cell, which happens to be 1. Therefore the net contribution or the net content of this larger cell is 2 plus 1, which is 3, which is what we would expect, because the original cell was a primitive cell and this is 3 times larger in area. Therefore it is not surprising that this is a triply non-periodic hexagonal cell. Now this is not the conventional cell which we use, and the reason is very obvious. The conventional cell is a parallelogram, has to be a parallelogram in 2 dimensions, and in 3 dimensions, as we shall see, it is a parallelopiped. Okay. Since this hexagonal cell is not a parallelogram, this is not the typical unit cell we would use for the description of an hexagonal cell, but the importance of this kind of a cell comes into picture when we want to understand the hexagonal symmetry. In other words, this cell has a hexagonal symmetry which the smaller primitive unit cell which lacks this kind of an hexagonal symmetry. So to summarize the important points of this slide, the hexagon shaped cell, often which is shown in many textbooks, is chosen to illustrate the 6-fold symmetry which this lattice has. And we have to be absolutely clear, this is not a conventional or the typical choice of a unit cell, and this is triply non-periodic or triply non-primitive unit cell term. It's triply non-primitive unit cell. It is 3 times in area as compared to the blue unit cell, and therefore it has got a net area which is 3 times, and its content in terms of lattice point is also 3 times. The 5th 2-dimensional lattice which we shall consider now is the general parallelogram lattice. In other words, in this case there are no constraints either on the lattice parameters a and b or on the included angle. The 5th lattice we consider, which is the final lattice in 2 dimension, is the general parallelogram lattice. The general parallelogram lattice has no constraints as far as any of the lattice parameter goes, A, B and alpha all can take any of the possible values. The unit cell is a general parallelogram, and on the right hand side of the figure the unit cell is shown in a larger figure. Now when I look at this lattice and when I overlay the symmetry operators as before, I can see that this lattice has only two-fold rotational symmetry operators. This is the minimum a lattice in two-dimensional has, which is a two-fold. Hence this brings about two important points. Number one, even though the parallelogram lattice is the most general or the lowest symmetry lattice, it still has two folds, and the other point being any two-dimensional lattice would have two-fold symmetries. So where are the two folds located within the unit cell? As shown on the right hand side, they are located at the vertices, the edge centers and also the face center or at the center of the site. All the symmetry operators within the unit cell are shown on the figure on the right hand side, and you can clearly see that there are symmetry operators at the vertices, the edge centers and also at the face center. If I want to give a shorthand notation for the symmetry of this kind of a lattice, all I can say about it is it has got a two-fold rotational symmetry, and clearly this lacks any higher order rotational symmetry operator like a three-fold, a six-fold or a four-fold, and additionally there are no mirror planes in a general parallelogram lattice. So to summarize, what is a general parallelogram lattice? It is a lattice which can be obtained from, for instance, a square lattice by shearing the lattice and also distorting it along x and y directions in any free manner, and in the process we find that the lattice parameters A, B and alpha all can take values which are not constrained in any way. Alpha can take any value, A and B need not be equal to each other or in any other way be constrained to have a certain value. The unit cell is a general parallelogram. In other words, a parallelogram means the opposite sides are parallel, but it is not a rhombus lattice as in the case of the previous example we considered, which was the 120-degree rhombus lattice. This kind of a lattice has only two-fold symmetries, and the two-fold symmetries have been overlaid on the unit cell as shown in the figure on the right hand side. Now let us summarize all the 2D lattices and look at their symmetry, look at the shape of their unit cell and also consider their lattice parameters. One thing, and additionally there is a table at the bottom which tells us that which of these lattices have centering possibilities and which of them do not have a centering possibility. So the lattices in two dimensions are the square lattice, the rectangle lattice, the centered rectangle lattice, the 120-degree rhombus lattice and the parallelogram lattice. The symmetry is possible. The square lattice has a 4 mm symmetry, the rectangle lattice has a 2 mm symmetry, the centered rectangle lattice also has a 2 mm symmetry, the rhombus lattice has a 6 mm symmetry and the parallelogram lattice has the least possible symmetry for any lattice, which is a two-fold symmetry. One point which we have been making so far and we will repeat again and again because this is really a point of confusion is the fact that often we use unit cells to describe lattices, but in no way these two should be confused. The shape of the unit cells which we can choose, and the typical unit cells chosen are, for the square lattice we choose a square unit cell, the rectangle lattice we choose a rectangle unit cell, and the rectangle unit cell is also chosen for the centered rectangle lattice. For the 120-degree rhombus lattice we choose a 120-degree rhombus unit cell, and finally for the parallelogram lattice, which is the most general possible, we choose a parallelogram unit cell. The lattice parameters and the constraints which we had considered so far is also summarized in this table, and we can clearly see that for the square unit cell A is equal to B and alpha is not equal to 90 degrees. For the rectangle unit cell A is equal to B and alpha A is not equal to B, but alpha is still constrained to be 90 degrees. So it is for the centered rectangle lattice. For the 120-degree rhombus lattice, A is equal to B, but alpha is equal to 120 degrees. For the most general possible parallelogram lattice, there is no constraints either on A or B or on alpha. Just to summarize the data above in a different form of a table, we consider the table as shown in the figure below, and the table shows you that for the square, for the 120-degree rhombus and the parallelogram, there are no centered variations of the lattice. The centered lattice is possible only in the case of the rectangle lattice. Before,
so how it is possible?
Yeah, so we will so in the audience here I have student, and Mr. Patel has a question, why is that only for the rectangle lattice we have the centering possibility? We will consider this, all the possibilities, and why some of them are possible in the coming slides in a lot of detail. Let me review these lattices we have done so far before I progress into some further considerations about these two-dimensional lattices. So let us start with the stage where we try to construct a two-dimensional lattice, and we said there are 5 distinct two-dimensional lattices. There are no more possibilities, there are just 5, no less possibilities. So that has to be absolutely clear. This is, and these lattices are generated by 2 translation vectors which are non-collinear, because if they are collinear, they cannot spread themselves out in 2 dimensions. There are 3 lattice parameters which go on to describe a lattice in 2 dimensions. These are 2 length scales A and B, and there is an included angle between the 2 which is typically given a symbol alpha. In the example shown in the figure, this alpha has been constrained to be 90 degrees, but in no way we should mistake that lattices always need to have this included angle as 90 degrees. This is just a starting example. Another point we considered, that there are 4 typical unit cells which we can use to describe these 5 lattices possible in 2 dimensions, and these unit cells are the square, the rectangle, the rhombus, and the general parallelogram. Further, what we did was that we tried to sort of put these 5 possible unit cells in terms of the expenditure on the parameters. In other words, if I make more expenditure on the parameter, it comes lower down in the list, and I assign it a value which is known as the terseness. If a unit cell is low on expenditure in terms of the lattice parameters, it is placed above in this list, and it has a lower, it is, in other words, terse, it has a lower value for the terseness. And in doing so, we also understood, for instance, in terms of expenditure in terms of lattice parameters, the square and the rhombus are at the same level, which have a terseness value of 1. So what is this terseness value? It is the difference between the number of parameters which go on to describe a lattice, which is 3 in 2 dimensions, minus the number of constraints which are imposed for a certain kind of lattice. For instance, in the square case, there are 2 constraints, and these constraints are A equal to B and alpha is constrained to be 90 degrees. In the case of the rhombus lattice, the constraints are A equal to B and alpha is equal to 120 degrees. And in both cases, I get value 3 minus 2 is equal to 1. 3 minus 2 is equal to 1. Therefore, the square and the rhombus are in the same level as far as expenditure in parameters goes. This is merely a classification based on expenditure in lattice parameters and has nothing to do with the symmetry concept, which is an independent concept we shall invoke later when we try to classify these lattices in terms of the crystal structures. The rectangle lattice, there is only one constraint on the angle. The A and B can take independent parameter values. Therefore, the terseness value for is 3 minus 1 is equal to 2. The parallelogram lattice has no constraints, and therefore C value is equal to 0, and I can therefore derive a terseness as 3 minus 0 is equal to 3, and therefore automatically the parallelogram unit cell lies at the bottom of this kind of an hierarchy. So we also considered these lattices in detail, and when we consider these lattices, we were focusing our attention on 3 aspects, and I will go to the board and write down these 3 aspects so that they are there for your reference. The first one being the lattice itself, the second one being the unit cell of the lattice, So, we focused on these 4 things when we were considering lattices. These are the lattice itself, which is nothing but an array of points, the unit cell of the lattice, and we had considered various shapes of the unit cells of the lattices. We overlaid the symmetry operators on the lattice, of course not extensively in order not to confuse the student, and on the other hand also on the unit cell. And finally, we also considered the shortest lattice translation vector, and we had pointed out this has an important bearing, especially when we deal with dislocations. So, I shall return to my slides now. So, when I consider the square lattice, I can see that it has got a 4-fold symmetry in addition to 2-fold symmetries. It has got mirrors. For instance, this unit cell shows a diagonal mirror and a vertical mirror. We said that when we write down the shorthand notation, I can call the diagonal mirror for instance as M2 and the vertical mirror as M1, and therefore I can write a shorthand notation for this in terms as a 4mm symmetry or 4M1 M2. I had also pointed out I need not write for instance the other diagonal or the horizontal mirror, because the vertical mirror is automatically taken to the horizontal mirror by the application of the 4-fold rotation axis. Similarly, one diagonal is taken to the other diagonal by the rotation or application of the 4-fold rotation axis, which is located at the center of the unit cell. We also noted, even though we always write A is equal to B, what we mean is that the modulus of the A vector is equal to the modulus of the B vector, but A and B vectors are actually distinct. And the important gist of the square lattice is the presence of this 4-fold symmetry, and if this 4-fold symmetry is absent, then we cannot call that kind of a lattice as a square lattice. In other words, the definitive signature of a square lattice is the presence of this 4-fold rotational symmetry axis. This 4-fold symmetry axis, it is to be noted, is located not only at the lattice points, but in addition at the point which is exactly between all the lattice points. In addition, there are 2-fold rotation axes which we noted, which are located at the edges of the cells or exactly in between two of the 4-fold axes. Now, when I have a unit cell overlaid with these symmetry operators, we noted that I don't have to do anything more, because this unit cell will now be operated upon by the A and B translation vectors to generate an infinite 2-dimensional lattice, and when it does so to the lattice points, it does so in addition to the symmetry operators. In other words, the infinite picture would have all the symmetry, all the lattice points and midpoints like here, having the 4-fold rotational symmetry. Now, we asked ourselves a question that why do we put symmetry operators on top of a lattice, and the answer to that, we saw that we are future going to consider crystals, and the classification of crystals is based on symmetry and not merely the lattice translation vector, which we had seen, which is the first requirement for something to be considered a lattice. In addition, we had made a point in the passing, of course we will return to it in considerable detail later, that if a crystal is based on the square lattice, it can have 4mm symmetry, which is identical to the symmetry of the lattice, or it could have a certain lower symmetry like a 4 symmetry. In other words, in such a crystal the mirror planes have been lost, but still if the 4 symmetry is present, such a crystal would be called a square crystal, otherwise it will not be called a square crystal. Just to reiterate the point, in other words, crystals which can be called square crystals should have at least the 4-fold symmetry surviving even after we have decorated the lattice with a motif to generate the crystal. So, even though we have lattices generated only out of translation vectors, we are very much interested in considering symmetries when we are dealing with lattices.
So, what is the main difference 4mm and 4 symmetry?
Mr. Patel has a very important question, that what is the difference between a 4 and a 4mm symmetry. This aspect we had considered when we dealt with the topic on symmetry, and perhaps we will come to it back again when we actually try to generate crystals. At that point of time, we will actually consider examples wherein there will be crystals with 4 symmetry, there will be crystals with 4mm symmetry, and it will be clarified beyond doubt that what kind of a motif will give you 4 symmetry and what kind of a motif will give you a 4 symmetry. So, it is a very good question, but we will return it to in considerable detail at a stage when we actually make these kind of crystals. The second lattice which we considered was a rectangle lattice, and the rectangle lattice had nothing but 2-fold axes, but more importantly the constraint between a row of in the vertical direction and the row in the horizontal direction, which are nothing but the A and B directions, is 90 degrees. So, this is later on we will see that the signature of parallelogram lattice is also a 2-fold, but this is a special kind of a parallelogram lattice wherein the angle which has been constrained to be 90 degrees. The centered rectangle lattice is a variant of the rectangle lattice, where in addition to the lattice points at the corners there is one at the center. Now, if you look at it, we could have described this same lattice by a primitive unit cell which is the shape of a rhombus, but typically we would prefer to use this kind of a rectangular unit cell, and we have to be clear here that our choice of the unit cell is not going to affect the lattice in any way. The lattice exists because of the surrounding that which is around each point. If you have a point here, you can clearly see in the case of the normal rectangle lattice, you had a point. If you want to reach the next point, for instance the diagonal direction, you had to go A and B direct vectors, while in this case you can actually go A plus B by 2, which is the shortest lattice translation vector which we had considered. So, it is the surrounding of each point which determines the kind of lattice, and it is not the kind of unit cell we will choose to represent this lattice, as exemplified very clearly by this green unit cell. And we had also, when we had dealt with the concept of unit cell, we had said that we could actually choose doubly non-primitive, triply non-primitive, and the choice is infinite, but those infinite choices in no way affect the kind of lattices which are possible in 2 dimensions, which is constrained to be just 5. So, there are only 5 possible lattices in 2 dimensions, and our choice of unit cells is infinite even for a single given lattice. But the preferred lattice in the case of the centered rectangle is a rectangle unit cell which has been shown in blue. The 120 degree rhombus lattice was, as the word rhombus implies, has a lattice parameter A equal to B and alpha equal to 120 degrees, and the important signature of this kind of a lattice is the presence of the 6-fold symmetry. So, of course, such a lattice in addition to the 6-fold symmetry has 3-fold axis as well, which we had told is of secondary importance because that is not the primary signature of this lattice. Nevertheless, if a lattice which is present, which is shown in the unit cell on the right hand side, it will have 3-fold axis and also the 2-fold axis which are shown in green color. This position of the 3-fold axis at the centroid of the triangle, which is half the unit cell dimension. An important question which we asked is that there are sometimes representations of the rhombus lattice without the 6 folds. How is this possible? So, we will answer this question in some little detail a little later. We had pointed out the shortest lattice translation vector was along the diagonal of the rhombus unit cell, which has a length of A plus B vectorially added. In terms of the mod of the length of the vector, you can clearly see the modulus of this A plus B vector is nothing but equal to A or B. So, in terms of length it is same as A or B, but in terms of vectorial addition it is A plus B. We had also considered an alternate possibility in terms of the cell to describe this kind of an hexagonal lattice, which was the hexagon shaped cell, and we had pointed out it is 3 times in area, 3 times in terms of its content of lattice points, and it is not the conventionally chosen unit cell to describe the hexagonal lattice. But there is a reason why we would sometime want to consider such a triply non-periodic hexagonal cell, and the reason is that this brings out the definitive signature of the hexagonal lattice, which is nothing but the hexagonal symmetry. And since unit cells are generated by merely translation vectors, I cannot go from this cell to this cell by merely translation. I need to rotate. This implies clearly this is the composite of 3 unit cells and not a single unit cell translated to a new position. So, in no way is my description of the lattice altered by this alternate choice of a cell which is triply non-primitive, but we should keep in mind that this brings out the hexagonal symmetry. The least symmetry lattice is the parallelogram lattice. Of course, as you can clearly see, when I mean least symmetry, I am talking in a double language, because in terms of the symmetry operators it has also got the two folds exactly like the rectangle lattice, but in terms of expenditure of parameters it is more. Now we have no constraints either on A or B or alpha, and in the rectangle case there was a constraint on alpha to be 90 degrees. This kind of a lattice has no mirror planes, and the only possibility here is the two folds. We had noticed that the rectangle lattice still had mirror planes. We also went on to summarize the 2D lattices, and the important thing we said was that the only kind of lattice which shows a centering possibility was the rectangle lattice, and as Mr. Patel has asked, why is that there is this possibility, and we answered that we will consider that concept also in a little more detail. The first question we will answer now is that why is that sometimes we see a representation, and you will have to refer to the figure at the bottom, a representation wherein you have no 6 folds and still you see that the unit cell is the conventional 120 degree rhombus unit cell. So, this poses some mystery, and as we had previously seen, the one which is the complete overlaying of symmetry operators on the unit cell is the figure on the top, which contains the 6 folds and in addition also the 3 folds. If you can look at the figure at the bottom and compare it with the figure on the top, you would see that the 6 folds have been replaced by 3 folds, and in addition you will notice that the mirrors, the cell edges were mirrors, and in the case of the hexagonal lattice are also missing here. There are these original vertical mirrors which are present, there are these inclined mirrors, the 2 inclinations, which are nothing but the 3-fold rotation acting on any one of these mirrors. So, if you have a mirror like this, if it is rotated by 120 degrees, which is the signature or which is the modus operandi of the 3-fold axis, then from this vertical mirror you can go to this mirror by mere action of the 3-fold axis. But you would notice that those mirrors are present in the alternate diagrams which you might have seen, but these mirrors which were at the edges of the original unit cell are missing in the case of the alternate representation. Now, the point we need to note, and I will read the slide for you. We know that lattices have the highest symmetry, and hence a 120 degree rhombus lattice always has 6-fold symmetries. Okay. We need to note that crystals based on a lattice can have lower symmetry. When I say can have, it means that it can have equal symmetry, but also can have lower symmetry, which then there is a possibility, since there can be a lower symmetry one, there are only 3-fold symmetries present. Now, when we are talking about crystals, so when I have this kind of a lattice, it has to have this kind of an hexagonal symmetry, but when I try to make a crystal out of it, for instance, there is a crystal which I have constructed here by taking the 120 degree rhombus lattice, but by putting an additional triangle on top of every lattice point. So, now my lattice is the usual 120 degree rhombus lattice with hexagonal symmetry, but I am putting a motif to make a crystal. And what is the motif? The motif is a triangle. Now, if I try to look at the symmetry of this kind of a crystal, now I am looking at the symmetry of this crystal and not merely the symmetry of the lattice, then I clearly see that this crystal has no 6-fold rotational symmetry. It has only got 3 folds as shown in the figure on the right hand side. Therefore, the original 6-fold symmetry which was sitting at every lattice point is now been lowered, and it has been lowered to a 3-fold. And why has it been lowered? It has been lowered because now the motif has a lower symmetry. We will actually explore this concept of putting a motif and lowering of symmetry in considerable detail later, but at this point all I want to point out is that if you have a lattice and in this case specifically the hexagonal lattice in, or which has been called a 120-degree rhombus lattice, then such a lattice will definitely have 6-fold symmetry axis in addition to the 3-fold. But when we try to make a crystal out of it, and in the specific example we are having on the slide here is by putting a triangle at each lattice point, and one of the constraints we said when we put a motif onto a lattice was that the motif should not be rotated or translated with respect to the lattice point when we go from one lattice point to the other, which is what exactly we have done here. And when I do that and make a crystal, the crystal itself has a lower symmetry as compared to the lattice from which I started off. Now if I want to overlay on the unit cell the symmetries of this crystal, now those are shown in the figure at the right hand bottom, and those symmetries have no 6-fold there, they are only 3 folds, and which is what sometimes you would see in textbooks. And what we need to understand when you look at such a figure is that it has been additionally added in so that you can understand crystals based on the 120-degree rhombus lattice, which can come under the class of the 120-degree rhombus crystal. Now there was an additional possibilities which crystallographers could have taken recourse to. What they could have done was that they could have generated an additional type of crystal. For instance, they could have called something called a triangular crystal, which are crystals with 3-fold rotational symmetry. In other words, you would have had crystals with 6-fold rotational symmetry, which you could have called, for instance, the hexagonal crystals in 2 dimensions, of course, and you could have used those crystals with only 3-fold rotational symmetry as triangular crystals. But unfortunately, there are no separate terms for the triangular crystals. They have been merged with the hexagonal crystals. Since there is only one term for hexagonal crystals, those hexagonal crystals contains those which have 6-fold symmetry and those without 6-fold symmetry. An interesting point to note is that I have used the term hexagonal, and for instance one example would be the hexagonal close pack crystal can be considered as a 3-dimensional analog of this 2-dimensional hexagonal crystal. Actually, to be more precise, I will have to consider a hexagonal lattice, which is nothing but an hexagonal 2-dimensional hexagonal net which has been grown in 3rd dimension to make a prism, and that is the hexagonal lattice. And a special case of that hexagonal lattice would be the hexagonal close pack crystal, which are crystals in 3 dimensions. So even though we had considered this example here, a lot of points and a lot of questions might be coming to your mind, and Mr. Patel has one question now.
Yeah, symmetry of crystals based on motif or only lattice? Actually here we change, if we want to change some motif, then symmetry I think of crystals will be changed.
Where is that the sentence?
So here trigonal is there, if we put some hexagonal, then
okay,
on the 3-fold we get 6-fold I think.
Okay. So the question you are asking, in other words, Mr. Patel's question is that how will the symmetry of this crystal change if I, instead of putting a triangular motif, I put a hexagonal motif? And in that case you will retain the very important question. So let me repeat the question again. I had made a crystal from the hexagonal lattice by putting a triangle at each lattice point. Now instead of putting a triangle, if I had put a hexagon, for instance a green hexagon at each lattice point, what would have happened to the crystal which I would be generating? Then in that case the crystal I would be generating would have a symmetry as shown in the top right hand figure, which would actually have the 6-fold axis and additionally those 3-fold and 2-fold axes. In other words, I would have had all the symmetries possible for the lattice. Of course, I need to be a little careful when I mention this, and it will become clear when we consider more examples, but I need to put this hexagon at each lattice point in a very careful way. I cannot randomly put this hexagon. I will assume that I am putting the hexagon the way exactly this hexagon is sitting on the lattice, in other words with the orientation such that the mirror planes and the rotations are coinciding with that of the lattice. I am not rotating it in a very arbitrary way as compared to the hexagon shown. If I do it that way, then I would get a crystal which has 6 mm symmetry, which is identical to the symmetry of the lattice. In other words, I would have not lowered the symmetry of the lattice when I go from the lattice to the crystal. A very important question, But we will return to this question and many more such questions which will be coming to your mind when we consider more examples of how we are going to put motifs onto lattices to generate crystals. At this point merely this was an example, so that when you are reading textbooks and considering especially these two-dimensional lattices, you should not get confused by a representation which has only threefold axes shown on the lattice. We had asked ourselves a question previously, that why are some of the two-dimensional lattices missing? Like for instance, we could have had, in other words, there is no centered square, there is no centered rhombus, there is no centered parallelogram lattice. Why is that these lattices are missing? We had implicitly answered this question with regard to the square lattice, but we will consider this example again and we will start from there, and we will answer this question for the other cases as well. In doing so, we will repeatedly invoke the concept of the unit cell and try to understand the lattices based on the unit cell. But again, to reiterate, lattices exist independent of the unit cell, and there are distinct classes of lattices which are based on translation vectors and identical surroundings to each lattice point, and that is the criteria when we try to understand lattices. So let us start with the case of the centered square lattice. And this we had seen before, that the centered square lattice is nothing but a simple square lattice. In other words, if I were to draw this picture of this lattice by rotation of 45 degrees, then I would be viewing it, the vertical direction would be this, and actually I would see it like a normal square lattice. I have two choices to make, either a doubly non-primitive unit cell or a singly non-primitive unit cell. And when we dealt with the criteria of choice of unit cells, we said that first is symmetry and second is the size. And if of course size and symmetry criteria fail, we would go for some kind of a convention. Since the symmetry of these two unit cells is identical, the size factor tells us that we should actually choose a smaller primitive unit cell. The doubly non-primitive unit cell has double the area of the blue cell, which is the primitive unit cell, and therefore when I am trying to talk about a centered square lattice, I am actually not generating a new type of lattice. All I am doing is viewing the old lattice at a certain angle. So in other words, there is not a separate case at all. So in other words, the centered square lattice is nothing but a simple square lattice. Therefore, I don't have to make a new case for this case of the square lattice. Now let us consider the case of the rhombus lattice, because we don't consider the second type of lattice, which is the rectangle lattice, wherein there are two distinct cases, the normal rectangle lattice and the centered rectangle lattice. So for the case of the centered rhombus lattice, why is that we don't have a separate entry, something called as the centered rhombus lattice? So let us look at the centered rhombus lattice, okay, wherein, just for sake of clarity, I have shown the centering points in orange color. We should note that actually lattice points are zero dimensional, therefore they cannot have color, taste or any one of those attributes which we associate with physical objects. They are mathematical entities of zero dimensions, and therefore they cannot have color as well. But I have just shaded them, like I have used a finite kind of a circle, filled circle to represent lattice points. I have used a different color, but please note they are all lattice points equal to each other. Just for the sake of clarity, the orange lattice point is the one which is being generated by taking a normal rhombus unit cell, but by putting an additional lattice point which is now orange in color. Now if I look at this rhombus lattice and now again look at this lattice viewing along the 60 degrees diagonal, I can clearly see I can construct two basis vectors which will go on to generate this new centered rhombus lattice. These are the A1 vector and the B, I should have made a maybe a B1, but doesn't matter. I call this a B2 vector. So I have an A1 vector and a B2 vector which go on to generate this centered rhombus lattice. Okay. In other words, what is this other lattice which I can now view along the 30 degrees or the 60 degree angle? It is nothing but a simple rectangle lattice. In other words, when I tried to generate a centered rhombus lattice, I was actually not generating a new type of a lattice. All I was doing was generating a simple rectangle lattice. Of course, I could have lived with still calling this a centered rhombus lattice, but we can clearly see that this is neither preferred in terms of the new classification, which it does not deserve, but additionally if you want from the unit cell point of view also, this is a smaller unit cell. The green unit cell is smaller than the blue unit cell, and therefore I would stick to my older classification, wherein I will call this a simple rectangle lattice, which is now generated by these basis vectors which are inclined with respect to the original basis vectors. So clearly the centered rhombus lattice has no independent existence. It is nothing but a simple rectangle lattice viewed in a different way. So based on the surrounding criteria, you see that this is a simple rectangle lattice. So we can now go on to the next kind of a lattice which is missing in the list, and that kind of a lattice is the case of the centered parallelogram lattice. We had noted before that the parallelogram lattice is the one wherein there is no constraints either on A or B or the included angle, and we had also said it is the lattice of the lowest symmetry. Now as before, what we will do is that we will color the centering point in a different way, and in this case we are going to give it an orange color, while the original lattice points are in this maroon or brown color. The original lattice was generated by these two basis vectors A and B, and now the centering point is this orange. And now I have this infinite lattice. Of course, a portion of it is shown here in this slide. We will, if you notice this a little more carefully, I can actually now define two alternate basis vectors, this red vector A1 and this alternate green vector B2, which can now go on to generate this new kind of a centered parallelogram lattice. Clearly, this new choice tells us that this is not a new case at all, because if you look at the relationship between A1 and B2 and the included angle, you will notice that it is exactly same as that for the parallelogram lattice. In other words, A1 is not related to B2, and in addition there is no special angle which would describe this kind of a choice. In other words, based on the fact that this unit cell is smaller than the blue unit cell, in other words this is primitive and this is doubly non-primitive, in other words the area of this would be half the area of the doubly non-primitive unit cell, it's clearly the choice of the green unit cell is better. And in order to state it differently, when I am talking in the language of lattices, this is not a new lattice at all, it is nothing but a parallelogram lattice wherein you have redrawn the basis vectors. So the centered parallelogram lattice is nothing but a simple parallelogram lattice, and when I want to make a choice of unit cell, I will go ahead and choose the green one in preference to the blue one. Hence this is also not a new kind of a lattice, and therefore our collection of lattices is not altered by these additional considerations of centering on the square, on the 120-degree rhombus, or on the general parallelogram lattices. Again, to emphasize the important point, we have used the shape of the unit cell to distinguish lattices, but lattices exist in totally independent of our choice of unit cell.